Welcome back to ECE 441A. In this segment, I would like to discuss how to design a phase lead controller using Bode plot techniques. We introduced this particular system in an earlier lecture, and we'll pick up with that information now. We're given a type 1 system, which means that it really, if we can stabilize the system in this block diagram structure with some G sub C, then we can be guaranteed that the steady state error due to a constant input is going to be 0. So our design spec is going to say, can we have a finite error due to a unit ramp? Can we track a unit ramp with some small error of 0.05 and at the same time achieve a phase margin of 40 degrees with a controller that's not going to slow down our system response, which means that we need a phase lead controller. The solution then, if we walk through the process or the steps that we've outlined before, the very first step is to actually find a gain value in our system, find K that satisfies the steady state error specification. When we're dealing with a unit ramp and a type 1 system, our steady state error is given as 1 over K sub V, where K sub V is our velocity gain constant. The velocity gain constant for a type 1 system is this limit as S goes to 0 of S times G of S. Remember, our G was this K over S, and in the denominator also a factor S plus 2. The result of then applying the limiting process to this expression allows us to quickly see that the S in the denominator gets canceled with the S in the S times G of S expression. We evaluate the expression, or we let S go to 0, and we're left with K over 2. We plug that expression for K sub V into our error steady state equation, and we wanted that to be less than or equal to 0.05 or 5 over 100. We can now solve that for K, and let's just go ahead and assume that we are interested in the lower bound. We don't want to increase our gain too much. K then becomes equal to 2 times 100 divided by 5, or 200 divided by 5, which is 40. With a gain of K equal to 40, our uncompensated transfer function G of S becomes K, or 40, S over S plus 2. That's the first step. We've now identified the gain in our system to achieve our steady state error specification. The second step is to actually sketch the Bode plot of this G of S. And this Bode plot is not that involved. We just have a constant term or a constant factor. We have a pole at the origin, and we have a linear pole factor with a pole at S equal minus 2. If we were actually sketching this by hand, then we would actually want to put this into time constant form. And now we have 20 over S times the quantity S over 2 plus 1. And you can see from this expression in time constant form, which you could probably see from the pole 0 form, the terms that we have a gain term, a gain of 20. We have a pole at the origin, That's the S by itself downstairs, and then we also have a pole at S equal minus 2 radians per second. Which really means for low frequencies we have a magnitude that's sloping at minus 20 dB per decade. It's coming down from the ceiling, and then it breaks one more time. This is our magnitude plot at omega equal to 2. We really just need to find where do we pin that magnitude curve down, and we can do that by finding some gain, let's say in dB, at a low enough frequency before we start breaking. So we just need to go less than omega equal 2 to find this. But let's now find a value for our gain curve in dB at a low frequency to fix that gain curve plot. In other words, I'm looking at g of j omega, which is now 20 over j omega, and then we have j omega over 2 plus 1. And if we look at a frequency of 1, the linear factor hasn't kicked in. Let's just go 1 decade before that, just so that we know that we're to the left or at lower frequencies than any breaks that might occur. The pole at the origin is always going to be on, which now says that for an omega equal to 0.1, we can look at g of j 0.1 equaling 20 over j times 0.1, and now we have j 0.1 over 2 plus 1. This allows us now to say that this particular piece is effectively negligible at that frequency, and now we can look at the magnitude of that. The magnitude of j is 1, and now we simply have that this is going to be approximated by 20 over 0.1, or 10 times 20, or 200. So that now the gain value at a frequency of omega equal to 0.1 is going to be 20 in dB, 20 times the log of 200, which we can think of as 20 times the log of 2 times 100. If we have this table of logs in our head, we can now just break that product of 2 times 100 into two pieces. We now have 20 times the log of 100. Let's do that biggest piece first, plus 20 times the log of 2. Log of 100 is easy. That's just 2. The log of 2, that's this table that we might want to have listed. That's roughly 0.3. So that now we have 40 plus 30% of 20, which is 6. So that now we have a gain of our system of 46 dB at a frequency of omega equal to 0.1 radians per second. So that now pins down our magnitude curve, meaning our magnitude curve is going down, and then it breaks at 2, and then it goes down even further, and now we've pinned a value at 0.1. This value is now 46 dB. And this would then be 1. Here is 2. And that should be 30% of the distance based on our logarithm up above. So here is now our 10. And this is now the magnitude curve as a function of omega. And our phase curve is maybe even easier to draw, because we had that pole at the origin, we know that our phase curve begins for low frequencies at minus 90 degrees, and then it's going to have one more linear factor contributing phase. That's a pole factor. That's in the denominator. It's going to contribute eventually minus 90 degrees more of phase. It begins introducing that phase with our straight line approximation a decade before the break. So our break is at 2 for that pole factor, which means that we have a phase curve that begins at minus 90 degrees. It's going to decrease, or it's going to break down in slope. It breaks down at a frequency omega that's a decade before the pole itself. The pole was at 2. We're now looking at the break happening in terms of our slope. It was flat. Our phase curve was flat at minus 90 degrees until we reached point 2. Then it's going to be sloping at minus 45 degrees per decade. So let me say, and stops. It's minus 45 degrees per decade slope a decade after the pole, which the pole is at 2, so it's going to stop its slope after omega equal 2 times 10, or 20 radians per second. Meaning our phase curve now is going to be flat at minus 90. This is not consistent with the curve that I just sketched. Unless I move back a little bit, maybe I should just a little bit. Let me go ahead and say that I now have identified, let's say 0.1, here's 1.0, here's 2.0, and we now know things are going to, whoops, not 2.0, 10, and now 100. We will have things happening at point 2. There is our pole at 2, but the phase moves smoothly right through that with the same slope. And then at 20 is when we will finally turn off. We're going to be flat at till point 2. Then we will go down to minus 180 degrees after a decade beyond our pole, and that's now the phase curve. We have the phase curve and the magnitude curve that we need to coordinate together in order to figure out what our phase margin is and if we need to change that. Let's now go to MATLAB and actually start to build up this Bode plot that we need. So now we're going to do a phase lead controller design with the system that we just identified. It's now a system with a transfer function. The numerator is 40 in the pole 0 form, and we had a pole at the origin and a pole at 2, which we can then represent as s squared plus 2s plus 0. This is now our system. It's a type 1 system. We can sketch its Bode plot. And it's sometimes easier to put a grid on that Bode plot. Let's look at that a little bit on a larger scale. And now we should be able to find that it's crossing 0 dB at 2, 3, 4, 5, 6, a little bit maybe beyond 6 radians per second. And at that particular frequency, we have a phase of something a little bit larger than minus 180. We do have a positive phase margin. It's, let's say roughly 20 degrees of phase margin, And we could, if we wanted to, have MATLAB tell us a little bit more specifically what that phase margin is by issuing the margin command. And now we can see that our phase margin is indeed 18 degrees at 6.17 radians per second. So let's now use that. Let me go ahead and take this curve into the workspace that I can work with and talk on. We've now identified our omega sub g. This is what we were calling our phase margin uncompensated. That's approximately 18 degrees, and I think in class last time you can see that we never cross the minus 180 degree line with our phase. So our omega sub p we don't have, which says that we now, for this system, we have a gain margin that's infinite. And that's actually what MATLAB was telling us. Now that we know this, we can move on with our steps of the controller design. One of those is to find our phase margin, which we just did. We actually sort of cheated and let MATLAB do that for us, but we found that our omega sub g is roughly 6.2 radians per second, our gain crossover frequency. We have a phase margin of 18 degrees for the uncompensated system, and we wanted a phase margin of 40 degrees or more. So there's our phase margin desired. We take away from that what we already have as far as phase margin and add in a safety margin. We now have 22 degrees plus 5 degrees, or 27 degrees is our desired angle that we want our controller, this combination of zero and pole, to contribute in this compensated system. Now that we've identified the phase that we need, we can calculate or compute the pole zero separation that we need, which is alpha. That's now 1 plus the sine of 27 degrees over 1 minus the sine of 27 degrees. If we compute that, we end up with our pole and zero being separated by a factor of 2.66. Then step number 5 is to actually find on our magnitude graph the point where the magnitude curve equals minus 10 log of 2.66 in terms of what frequency does that happen. We now are looking on this curve, where do we actually have, or what frequency is our magnitude plot minus 4.25 dB. So if we go back up to our curve here, we are now looking for there's, let's say, minus 4.25. We read over, or we lay a ruler down, and now we can see that that's going to occur at this frequency right there, which is, let's say, an omega sub m of 8. So now we've seen that based on this formula of minus 10 log of alpha, we've now identified our new gain crossover frequency to be 8 radians per second, and that's actually where we will be geometrically centered with respect to our pole and zero of our controller. So with that centering, we can now find our time constant, tau, of our pole, which is now 1 over omega sub m square root of alpha, which is now 1 over 8 square root of 2.66, and our tau now becomes 0.0766. Our pole is now 1 over tau, which is 13.05. So we may just approximate that to be 13. Our 0 is an alpha factor smaller than that, so that we now have this 1 over alpha tau. It's another way of expressing it, but we have 13.05 divided by 2.66. That's the p divided by alpha. That's now 4.9, and now we have a controller, G sub c. In terms of zeros and poles, we have a 0 and a pole, and we've just now found what those values are. Our 0 is at minus 4.9, and our pole is, let's say, at minus 13. We can now put that into MATLAB and see what we end up obtaining. So now we have a controller transfer function, which is the numerator is going to be 1 divided by our pole, comma 1 in time constant form. Our pole factor is 1 divided by our pole value, which we said was 13 in pole 0 form. So this is our phase lead controller transfer function. We now want to combine that, and we could check that if we wanted to. We could say, what's the 0 of our controller? We could say z sub gc is the 0 of gc, just to double check that we're doing things right. And we could say the pole of our controller is the pole of that transfer function, and it's at minus 13. We now want to combine that compensator or controller with our plant, and this is what I'm calling the loop gain. And we can now try to sketch or find what is the stability margin associated with this compensated system. And in fact, we do get a phase margin of 41 degrees. And again, we maintain a gain margin of infinite because we haven't changed our effective pole 0 excess. So we now have a compensated system that indeed is meeting our design specification as far as the air steady state was met by our gain, and then we improved the phase a little bit, or the phase margin, from 18 degrees to 41 degrees by the introduction of this controller. We could even compare the two different Bode plots, the uncompensated Bode plot. Let's say that we will sketch with a blue line, and we'll sketch our compensated Bode plot with a red line. And that's now our difference between the compensated and uncompensated behaviors in this particular phase lead controller design. Now, if you wanted to, you could actually maybe look at the closed loop transfer function and look at where the poles are, and we could even look at maybe the step response and the response due to a ramp if we wanted to look at the time domain behavior associated with this controlled system. Let's now go back to MATLAB and look at the closed loop transfer function. That's going to equal the feedback, unity output feedback with this loop gain. And with respect to that, we could say where are the poles. Those are now at some imaginary parts, -4 plus and minus J7.7. That's going to give you a zeta value that's less than 0.7, and we do have a third pole at -6.8. And now let's look at where our 0 is for the closed loop. We could say 0 of CLTF. And it's at -4.9. So we not only have 3 poles, but we also have a finite 0. We could look at the step response of that closed loop transfer function pretty quickly. And there is now what we have relative to our step response for this system. And maybe what I could have done is I could have actually on that plot, maybe I should do that before I can right mouse click and find the characteristics. I could get the peak response and identify when that is. So now I have a 32% overshoot, and it's occurring at a time of 0.372. Maybe I should just include that and not this one in the notes section. So there is our step response, which we knew that it wouldn't have the best overshoot properties because of the angle of those two complex poles, plus we had the 0 at -4.9. Now, if you wanted to, we could even potentially look at, so we see that we have a transient that only lasts for about 1.2 seconds. Let's now see if we can generate the ramp response. So let's now build up a time horizon from 0 out to 2. We know that that will be sufficient relative to our transient. We now are going to do a linear simulation of this system relative to, so there's our closed loop system, relative to the ramp, which is really just what we've called t, and we're going to do it over a time horizon of t. So this is the output ramp response. This is a unit ramp that we're applying to our system. And I didn't display that. I hid it with this semicolon, and now what I want to do is go ahead and plot the output y, and let me go ahead and make that red. And here is our reference ramp signal, and I'll make that blue. And there is now our ramp response, and I can label that up and clean it up a little bit better. But now you can see that we do have a brief transient until we reach a steady state, and then we get locked on to that ramp, and you can see that we do have a steady state error while that system is trying to track that ramp signal. hopefully that now helps you with building phase lead controllers using the Bode plot technique.